Welcome to the fourth in a series of lessons on the engineering design process. Today we're going to be talking about how to create and select concepts for a design. So what is conceptual design? As you can see, conceptual design occurs after we've defined the problem. We will have generated ideas before we begin creating concepts. Conceptual design is really coming up with a broad outline of the features and functions of a solution. We identify the components of the system and how they interact with one another. We also confirm that the systems that make up our overall solution integrate together and will meet the needs of our stakeholders. When we finish conceptual design, we should have in hand rough sketches or models of what our solution is intended to be. A definition of what the major components are, or the systems within this overall solution, and the definition of interfaces that will enable these different systems to work together as we intend. Let me give you a quick example of what a conceptual design might look like. Here we have a model of a design for a bottle positioner. It's to grab a bottle, turn, position it, and place it in another location. Included in this conceptual design would be major structural members that are going to be used to guide this movement. Other mechanisms like this grabber that could actually accomplish a task like holding on to the bottle. Mention of the power that's going to be required, and here we see that we have motorized turntable and lift that require power. And sensors that would be part of the overall solution. Sensors here are used to monitor rotation of the turntable and also to detect whether or not we have a bottle in the grabber. Going along with this sketch, we would have a narrative explaining how this concept would function. Here we see that the handler would use a grabber, a 4-bar linkage, a turntable, and so on. These various components working together to accomplish the overall performance that we intend. So what are the purposes of doing conceptual design instead of just charging into the development of a finished solution? Why should we do conceptual, or sometimes it's called systems design? First of all, this gives us an opportunity to get agreement among our team members on what the rough design is for this whole solution. You probably would have multiple people working on different systems in your design, so it's important to bring them together and get agreement on how they will all fit together before moving forward. As mentioned earlier, it also is a way of demonstrating that the individual systems are going to fit together, and of course we mean also work together. As mentioned earlier in previous videos, the earlier we detect flaws, the better. So here we have an opportunity to identify any flaws in the system, individual systems, or even in system integration, how they come together. So it's important that we do this well. It also provides an opportunity for a formal review. Perhaps you've heard of design reviews, where there's a formal review of the design at the given stage. Here at Conceptual Design, we have the opportunity for a conceptual design review that decides whether we go or no go, whether we've completed that stage or phase of development adequately to move on to the next phase. So it's an important milestone for us in the overall design process. What do we mean by system anyway? And using that term, system is simply a set of things that work together to perform a function. When we're dealing with robot design, examples include a delivery system, system for collecting game elements, system for propelling or propulsion system for the whole robot, etc. So for your given design, you'll have a number of systems that need to be defined and then integrated together for this conceptual design. Really, our conceptual design must define and integrate all the major systems in order for it to be complete. What are the steps then in completing a conceptual design? First of all, we need to identify those major systems that are part of the robot. This probably includes things like the chassis, the main game element for the game, how you handle that, collecting and scoring it, systems for that. You'll have autonomous scoring opportunities. So for those, you'll need ways to detect and position and score system to complete those functions. In the end game, you also have other opportunities for scoring. So your conceptual design should include the systems or apparatus used for doing the end game scoring. You also need to consider things like the control system for these different systems, sensors, how you power, move devices, and so on. You also need to consider how you allocate the resources to these systems. Your team is limited in terms of the resources that you might have, or perhaps there are game rules that limit you. Of course, your space is limited, so an important part here in system design and conceptual design is allocating space for the different systems that you envision on your robot. Here we've identified a certain space for the chassis, for the collection system, for delivery, and so on. Also, you need to consider the number of motors available. For FTC games, you're allowed only 8 motors. So how many will be allocated to chassis, delivery, collection, and so on. Of course, there are also issues of sensors, the electronics, what sensors are available and which ones are available perhaps for different systems within your overall design. So you identify the systems, allocate resources, then we move on to developing the concepts for each of these systems, and then integrating the systems into a whole. Each of these steps is very important. A tool that we find useful for defining systems is called a morphological chart, or a morph chart for short. It's simply a way of showing the different options we have available, the different ideas we have for different functions, so that we can put them together into reasonable combinations to make up concepts for a given system. Let's say we're talking about a system for scoring game pieces that come in multiple sizes. The functions that we might need in this system could be collection system, a way of storing up to, say, 3 pieces, a way for sizing or sorting those pieces that are collected, and a way to actually deliver these into bins. So, assuming that we've done some good idea generation and screening ideas so we know which ones really have some potential, We then can list these ideas for each of these functions. For example, for collecting, perhaps there was the idea of using a scoop, rotary brush, maybe a combination of the two, maybe a paddle wheel, and so on. So you could have a number of different ideas that have some good potential. Again, for storing, you could have different ideas and so on. Putting a concept together requires that you identify compatible sets of ideas. So perhaps a scoop that then places the game pieces onto a conveyor. The conveyor perhaps has holes in the floor that allow different size pieces to drop out at different points. And it continues to convey these pieces until they reach the bins. So this could be one concept, and you come up with many other combinations. When you've identified what you think it might be a reasonable concept, give it a name, because you'll have lots of concepts. You need to remember what some of the features are of that concept, so you'll be able to compare them well in subsequent steps. Let's look at some concepts that we might develop for a ring handling system. You'll recall from previous lessons that we had a game where we're scoring rings by placing them over pegs. So let's look at how some concepts might be put together for a ring handling system. Let's talk about an individual ring collection and scoring system. So we're collecting only one ring at a time and then attempting to score it on the peg. We identify the features or functions that are important for this system. Here we have three. One, ring collection from the floor. The second is to then elevate and reach in order to position the ring appropriately near the peg. And finally, the ring placement onto the peg. So you identify the functions and then list the ideas that have been identified that have potential for being effective for ring collection, for the ring elevation and reach, and for the ring placement on the peg. Then with these available to us, and there could be many of these, we identify some suitable concepts. One might be taking the scoop that's assisted by a rotating brush, and that's then mounted on a vertical slider and 4-bar linkage to position near the peg, and then finally tips to slide the ring onto a peg. So that could be one concept. The second one might be using the scoop with rotating fingers to assist it, now using an inclined slider to position, and then tipping onto the peg from the side. The third one might be using some kind of a grasping clamp to grab the ring, then an arm that extends and pivots to position, and then dropping the ring from above the peg to get it on the peg. And the fourth one might be a scoop aided by a soft roller and then tossing the ring to get it on the peg. So each of these four could be a concept that we might consider further. With a list of concepts available, we need to evaluate these. So how do we do that? A common way is using a decision matrix, sometimes called a Pew matrix. And this is basically taking a list of concepts that we want to compare, then identifying the criteria that we're going to use for comparing these. And these criteria came from earlier exercises we did defining the needs based on our game strategy. We identify how important each of these criteria is, and then we score each concept with regard to how well it meets a given criterion. Notice here that we suggest scoring using 1, 3, or 9 points in order to really spread out the concepts in terms of the points that they have assigned to them. So this gives you better ability to discriminate the good ideas that are important, that meet important criteria, and separate them from the ideas that don't meet these criteria as well. From the numbers, the scores that we've identified, we calculate a weighted total score. That's simply taking the score, say for concept number 1, under criterion 1 we have 3 points, so it was kind of a mediocre meeting of that criterion. Take that 3 points, multiply by the importance of 3, gives you 9. Then going to the second criterion, it was scored 1, multiplied by 2 for importance, that gives you 2 more points. For the third criterion, it met it very well, so it had 9 points multiplied by 2, which is the importance, which gives you 18 more points, and so on. Add all these up and you get a total score of 32, a weighted score. So for each of these concepts, you'll have a total, and you'll be able to compare these to see which score the best. Here we can see the ones that scored best would perhaps merit being considered further for later steps in our concept development overall for the robot, but also maybe taking it further into prototyping. Let's look at an example how we might evaluate different concepts for this ring handling system. Recall that we had identified 4 different concepts listed on the left side. We identify some criteria for which I've listed here: scoring success, horizontal reach, collection speed, and control complexity. For each criterion, we have an importance rating, 1, 2, or 3. And we then score each of these concepts against the criteria, sum up the weighted scores for a total score, and we begin to see that there are some differences. Note also here that the different concepts have strengths in different areas. Some are stronger on the scoring side, some are stronger on the collection side. So for the system, one might look for ways to combine strengths from these different concepts, or maybe our consideration of these has given us some new ideas. So a new concept can be defined, added to this for additional scoring, and now using a scoop aided by fingers for collection, now modifying the incline so it's adjustable so that it can indeed reach further and score better, and then tipping the collection device to drop the ring on to the peg would be the way of scoring. So here we see that our scores become 3 9s and a single 3. The 3 shows that we've actually decreased or increased the complexity, so scored a lower score for complexity, because now we have the additional need to control the elevation of that incline. You see our score overall is significantly better, which says that this new idea appears to be a much better concept. Once we have identified and developed a concept for a system, it's important to describe or document that concept. So here for the ring handling system, one might develop a sketch such as shown here, and then make sure that the viewer, the reader, will understand the function. The rotating fingers are used to help pull the ring into the scoop. The scoop is then pulled along the cascaded slider until it reaches the end of the slider. At that point, the scoop is tipped, and when the peg is sensed, hopefully it's going to tip and drop the ring onto the peg. In addition to describing functionality, one should for this system identify the power and control features as well. Here we assume that a motor is used to power the extension of the slider. Servos might be used for powering the rotation of the fingers, for tipping the scoop, and possibly for adjusting the slider scope. So we've identified what resources, what servos and motors are assumed to be part of this system as well. We need to think about the interfaces. How is this system connected to or interfaced with other systems? This adjustable slope slider is going to need to mount on the frame, so it will need to have a pivot in some way, some mechanism for changing its slope. And also, since the scoop is going to pivot for dumping the ring, we'll need to make sure that the scoop is mounted on the pin and there's a servo mounted in such a way that it properly will tip that scoop. So in describing the system, we need a good visual, explanation of function, components, interfaces, things that help the reader understand what is intended here. Now, in order to document our understanding of a system before we try to integrate it with other parts for the overall design, let's go through a few steps that might be useful. First, I encourage that for each system, individual team members, perhaps pairs, or depending upon what's available, 1, 2, 3 people, might be owners for a given system. It's their job to present the system and defend it as we're attempting to integrate this into the whole design for the robot. These system owners need to know the following. How does this thing perform? How is it expected to perform? They need to know what are the strengths of the system, what are its weaknesses. So they need to understand how this performs. Secondly, they need to understand the resources required or consumed by this system. What space does it take up? They need to consider both when it's stored, and it needs to be below this 18 by 18 by 18 sizing, but also when it's extended in operation. What is the volume? What volumes will it sweep out and perhaps strike things that were not thought of? What is the weight that's estimated? What support structurally is important? Number of motors, sensors, servos, and so on. Also, they need to know what are the inputs, what's required for it to perform as intended. So for a ring handling system, there is a necessary orientation or positioning in order for the game elements to be approached or received. So they need to understand what is that orientation or way in which the game elements must be approached. They need to understand what are the sensor inputs that are going to drive it, what power inputs will enable it to perform its functions. And then what does it produce? How is this game element handed off? In this case, where we're talking about a game element handling system. How is it handed off? Does it throw something? Does it slide? And what signals does it produce? Does it give feedback? Does it give an indication that something has been scored, something's been received? So they need to be able to understand how it performs, what resources it needs, inputs to make it work well, and what outputs it produces when it's completed its function. With these different systems, we need to check to see that they are compatible with one another. So a good way to do that is to build a table. Identify the system, critical pieces of its performance, its inputs, its outputs, and see that we don't have things that are conflicting between one system and another. So if we identify 4 systems that are being considered for this particular robot, drivetrain, a collection system, a transport system, a scoring system, we need to identify the performance. Okay, the drivetrain, we expect it's going to be able to move forward, back, sideways, turn, etc. For collection, it's going to be able to pull a single ring into the scoop. It's important to note that single ring. That for transporting, the scoop is going to be pulled to the end of the slider. For ring scorer, the scoop will tip and drop the ring onto the peg. That's the way we're expecting these different components to perform. Everyone will understand this. Make sure that that is the performance that we strive for. What are the inputs? The drivetrain is going to have 4 motors driving the wheels. The controller signals are what instruct those motors to move one way or another and cause the motion desired. For ring collection, an input is to get the robot near the ring. It's a collection system, must be near enough to grab those rings. And also it needs to have the power to these rotating fingers to pull those rings in. The ring transport system needs power. It also would be helpful if this transport system had a signal that it received saying that the ring's in a scoop, you can proceed to the next step. So the ring scorer then hopefully could also be told by a sensor that the scoop is near a peg and it's in position for dumping, tipping, and then of course it needs power to tip. So each of these different subsystems may require signal to trigger something, power to perform something. It's important to identify what they need. And what are they going to produce? Notice that the drivetrain has to produce a position that's desirable and speed to get there quickly. The ring collection needs perhaps a signal saying that the proper ring is in the scoop. If you have the wrong one, you don't want to go off and attempt to score it. If you have too many or if you don't have one, so you need a signal saying that it's ready to go. And you know that the ring is transport ready. The ring transport system needs to be such that the ring and scoop are positioned where they need to be by the end of their function. And they produce a signal then that says, hey, we're ready to tip. And then of course the ring scorer tips and the ring slides off. So the output is the ring sliding on to the peg. You note the output of one part of the robot tells the next part to perform. It's important to see the relationships here so that we realize that there need to be signals, or the operator needs to be able to sense something in order to trigger the next step. So by putting all this information together, you begin to see what information is needed to cause the operator or some device on the robot to perform a step at the right time. Okay, so assuming that we've come up with a conceptual design, how do you present this? First of all, you want to give a model for the overall structure and behavior. For example, if we have ring collection and then we also have another way of scoring by turning a wheel a certain number of turns and so on, what conceptual design was produced to accomplish these scoring functions? We have a sketch showing the major components. We have a drive system, mecanum wheels, mecanum drive in this case, positioned where as indicated here. A ring handling system, again with the fingers to collect the slider and so on. And then for this additional scoring, by turning the wheel, we have another servo with prongs to turn a crank and to score in that way. So we present this conceptual design by showing the major systems, the principal systems that are part of this robot, and giving a bit of explanation as to what each of these systems is expected to do. So that's a way of presenting your conceptual design. What we need to include in this? Well, first of all, maybe it's good to just check that we've addressed all the ways in which we had intended to score. Have we addressed this autonomous? Perhaps we have a primary scoring option and maybe a secondary option. Does our conceptual design address the operator control scoring? A primary way and maybe a secondary way? How about endgame scoring, primary and secondary? And then, of course, if it addresses this, we need to think about other things that might be important for this design. How easily can it be repaired? Can we replace, remove, substitute parts? And the ease in which it can be controlled by the operator. Did we include ways the operator can know what's going on and be able to command the robot to do things at the right time? The goal here is an overall concept that will work as needed for the game strategies that we've identified. Remember, we're looking for some confirmation that this design is going to work, and we can develop it further without having to go back later and make changes. So, if we have conceptual design review, and I really encourage that bring in outside experts to review your conceptual design. What we're looking for from them is approval of the systems that you've identified, the overall structure of a robot and its behavior, and how that lines up with the game strategy. So they need to review that and see that that's appropriate. Need to look at the chassis, frame, drivetrain, and see that it supports the needs for mobility. Your autonomous systems, are they going to be functional and flexible? The operator control systems, they need to review and see that those can score successfully and be flexible in case conditions change. And do you have components that meet the game rules? Perhaps here's where the checklist comes along, we use that to ensure that we have met all the requirements on number of motors and suitable components that are able to be used for FTC robots. The reviewers are also asked, I would like to see them make a critical judgment. Is this conceptual design approved? Does it meet all the expectations so it's ready to move ahead? The team's ready to move ahead to the prototyping? Would they approve this but suggest some minor revisions? Or are there some problems that are serious enough they would not approve this conceptual design? You need to go back and perhaps come up with better concepts, better ways of integrating or something of that nature before moving ahead. So it's important for them to make a judgment like this to really keep our teams accountable, think critically, and prevent moving ahead when we're not ready. Ideally, the reviewers will also provide feedback. They'll explain concerns that they have and document those for the team, but also they might list specific revisions that are required, that they believe are necessary, and explain why and what needs to be done. Remember, the goal here is to find all the problems at this point before advancing to prototyping. So, documenting what we've done then for conceptual design. You want to design the concept, define each major system, perhaps a sketch or visual, labeling the important and unique features, explaining how it functions, presenting the integrated conceptual design that has all the major systems, again a sketch or visual for the entire concept or your design with labels, and explanation of the overall performance. It would be great to include in your documentation the documentation that came from your design review, the reviewers' judgments and their feedback to you, but also your reflection on what you received, evaluating what they've told you, what you've learned from the process, how you're going to proceed from there. So you have an opportunity here to document powerfully your conceptual design. So to this point, we've identified our game strategy. We've moved ahead with needs, ideas, and today we've talked about how we put together concepts and select the best concepts and integrate them into a complete conceptual design. Next time, we'll begin specifying requirements for the robot and prototyping, and that will take us further toward a completed design. Thank you for participating in this series. Hopefully this has been helpful to you, to your team. We look forward to seeing you again for the next lesson. And again, I'd like to thank FIRST for inspiring these kinds of events, which really are challenging and help us learn how to design and work together more effectively. See you next time.